Problem 7 asks you to evaluate the following indefinite integrals. Print your answer in the box provided. You do not have to simplify your answers or explain your steps. So this is a definite integral, so we're going to need to invoke the fundamental theorem of calculus part 2. And we want to calculate the antiderivative, and then we have to evaluate it at the bounds of the integral. So the antiderivative of e to the x is just e to the x. This is actually a small u substitution where our u for this particular piece of the problem is pi x, our du is pi dx, and since I don't have a pi in front of this problem, right, 1 over pi du is going to replace our dx. So when I anti-differentiate this, the antiderivative of negative cosine is sine, positive sine. Or I'm sorry, the antiderivative of cosine is sine. So I get negative sine pi x, but I have to put a 1 over pi in front, right, like I had for my du over here. So now if I check it by taking the derivative, I'll get cosine of pi x times pi, which cancels and gives me back what I wanted. So this needs to be evaluated from 0 to 1/2. So e to the 1/2 minus 1 over pi of sine, and when I plug 1/2 into here, I get pi over 2 minus e to the 0 minus 1 over pi times sine of 0. 0 and pi over 2 are known values on the unit circle. So e to the 1/2 stays e to the 1/2. Sine of pi is 1, so I get negative 1 over pi. Sine of 0 is 0, but e to the 0 is 1, so I get minus 1. So my final answer is e to the 1/2 minus 1 over pi minus 1. The second problem is going to involve u substitution, and I'm going to try and let my denominator be u. So if we try that, we get u is x to the 6 minus 4x plus 7. My du, when I calculate that, will be 6x to the 5th minus 4 dx. So now when I go back to my integral, I have that right here. So now when I translate my integral, I have 1 over u du. But my integral was a definite integral, so I cannot write 0 and 1 here, because the dx in the original integral is actually saying that this is x equals 0, x equals 1. So if you try to write a 0 and 1 here, you're actually saying u is 0 and u is 1, and that is completely false. So we can fix this by changing our bounds. And this is a really easy thing to do. So when x is 0, if I pick the bottom variable, right, I plug 0 in for x into my u equation, and I can see that u is going to be 7. So that means the 7 has to go where the 0 was in the original integral. When x equals 1, when I plug 1 into my equation, I get 1 minus 4, which is negative 3, and negative 3 plus 7 is positive 4. So 4 goes here. Now before I evaluate this integral, I notice that my bounds are backwards. We like them to be low to high for the fundamental theorem of calculus. So I'm allowed to switch them as long as I multiply the integral by negative 1. So this is now negative the integral of 4 to 7 of 1 over u du. So the antiderivative of 1 over u is natural log of the absolute value of u. And remember, when we differentiate ln of x, it's just 1 over x. But when you anti-differentiate 1 over x, it's the natural log of absolute value of x. So you have to have this absolute value here. We're going to evaluate this from 4 to 7. So I get negative ln of 7 minus a minus natural log of 4. So my final answer is negative natural log of 7 plus natural log of 4. I was able to reduce, or excuse me, I was able to drop my absolute value bars when I plugged in the numbers because those were both positive values. So the value of the natural log of the absolute value of 7 is the same as the natural log of 7. However, if you had left them as absolute value, that would have been perfectly fine.